Okay. So hopefully this one sheet helps out. I think I gave one or two problems that involve doing this process in the homework. One little thing, let's see. This kind of came up with someone I was talking with in office hours. There's that step where you replace the summation of I or I squared or 1 with what it is. So if you remember, like, if you end up with this, what's that? If you add 1 up n times, you get, remarkably enough, no. If you add 1 to itself n times, what's 1 plus 1 plus 1? For example, 3. So if you do 1 to add it to itself 3 times, you'll get 3. So if you add 1 n times, you'll get n. I like it. Definition of multiplication is only based on addition. N times 1 is n. So if you add all the numbers up themselves, this is that thing we did with the urban legend about Gauss. This is the one that comes out to be n times n plus 1 divided by 2. All those guys. And then there's one for I squared. And then one for I cubed, I think. I think it's as far as I went. Yes. All right. So there's the step when you... so if you have this handout, it's that step 1, 2, 3, 4. Fifth step, from 4 to 5. When you're rewriting the sum into a pure expression in n, that's with me. Okay. You know you're on the right track if in front of this you have something that's the same degree. Notice here, for example, I rewrote that sum of 24 as 24n, and in front of it there's a 1 over n. This one was n squared plus stuff, and in front of it was something over n squared. That kind of tells you're on the right track, especially with the functions we will be working with, are very simple functions. That type of thing is going to happen. If you don't have that, you've done something wrong, almost definitely. Okay. That's just one little thing that's a nice check as you're doing these problems. Trust me, I am very aware of how many steps go into this. But this isn't really, to be completely honest, not that difficult. It's a very recipe-ish kind of approach. The reason I do it is just to show you what goes into these things, what's behind the scenes as we get into integrals and what integration is. Okay. And the other, I think, yeah, there was another handout we did together that was related to the drawing of the rectangles and adding those suckers up. I like it. Yes?
For the homework, when you do the midpoint, but then you do the second midpoint, I guess. So you take the midpoints of those midpoints.
So where's...
I think, I'm not sure. I have done it online. I can ask you tomorrow about it. I'll look at it.
Does anyone else remember that problem he's talking about? I don't remember. There might be one that asks you to do that, but...
I can look at it. I can pull it up.
Yeah, I can remember that one. All right, let me know if you find it. All right, anything else from homework stuff? So we got through 4-9, 5-1, 5-2. I'm thinking about it. Okay. So what we're about to get into is huge. It's really important. And again, if you've taken any calculus, it's very possible that the point of getting antiderivatives and integrals to match. So what we've been doing so far is integration, which is finding areas under curves, right? And it's really tedious to do it this way. Yes. And to be honest, I did this one semester. Do you see how this is very specific with A is 2, B is 5? So it has a between 2 and 5, find the integral, find the area under there. If you did this with generic endpoints, or with one endpoint being 0 and the other endpoint being B, what's really interesting is at the end you end up with the antiderivative, which is not a proof, but it is an indication that maybe there's a connection between the area and the antiderivative somehow. That's the connection that we're going to try to make today. That's the main thing we're going to do. All right? If there's no other questions, did you find it? Or?
Yeah, I did.
Which?
So you first find the left endpoints for 3 of them, and then, or right endpoint for 3, right for 6, and then left 3, left 6, and then M3, M6. So for the second M6, do you just take, so...
Oh, I see. You just got to break it up into
Break it up again.
6 rectangles. Yeah.
Okay. Right.
So yeah, you're right. The way you're saying it was trying to think ahead about how to find the. It would end up being the midpoint of the.
Okay.
Yeah. Okay. All right. Let's make sure I didn't forget anything. Okay. I like that. So I want to really make sure you guys understand what we've done so far. So finding the area under a curve on the surface sounds like it should be relatively easy, but it all depends on what that curve shape is. If the shape is just a flat line, then it is remarkably easy. It's just rectangles. It's actually rectangles. So then the area, I don't have to do any weird shit. I can just get the area just by using geometry. The same would be true if I had, like, the function was 3x. And I want to find the area under f of x from 0 to 2. So what shape would play out here? 3x is going to go from 0 to 2, it's going to go from 0 to 6, right? And I want to find the area underneath that, so of course that makes a triangle. So there's a whole section in here of the homework that says use geometry to find the areas described by this, right? So we have gone past this process now in the lecture. You still got to do this in the homework if you haven't done these sections yet. But this idea, this, which is adding up rectangle areas, and I really hope my use of the word resolution makes sense to you guys. When we make the rectangle smaller, we're getting better resolution. It's sort of like the difference between 8-bit games and where we are today, with all the different kind of approaches to make graphics more realistic, all to make water look better on games. And that would be if I take this to infinite resolution, right? And there's that whole process that's on that sheet I gave out. But now, what symbol do we use to represent this? If I'm going from, in general, from A to B, the symbol would be integral A to B, f of x, dx. These mean the same thing. So how do I represent this question symbolically? It would be integral 0 to 2, f of x, 3x, dx. So that symbol, this collection of symbols means the area under 3x from 0 to 2. Right? A big part of mathematics is our attempt to consolidate what we're trying to say, which means that everybody that comes after has to learn the language before they can even do shit, right? Got to know what a square root symbol means before you can do it. So here you got to know what an integration symbol means, and then you have an approach. So if this was my question, I wouldn't even need to use calculus for this. I'd have to know a little calculus to interpret the question, but then I'm like, oh, it's just to find the area of this triangle. Well, shit, right? Is everybody with me so far? Okay. Now, things get much more complicated when the roof we're talking about, the function under which I want the area, gets all wobbly. Because then geometry goes, I don't have a freaking clue, dude. That's where calculus really steps in and says, I got this. All right, how we doing? Question. So, I mean, I can approximate. If the actual function kind of looked like this instead, I can say the area of the triangle is an approximation for it. Right? It's like an under approximation. You guys with me? So that's the whole idea of using rectangles, the most basic shape, to fill in the thing, make them less and less and less until it's infinite rectangles, and then I got it perfectly. What we're doing today now is to try to take a step away from that process, because that process looks horrendous if you haven't tried it yet. I don't blame you for that, for feeling that way. By the way, what would this be? What's the answer to this? What's the base? 2. What's the height? 6. So what's the area? 6. Square units, whatever they are. Right? Cool. All right. So like I said, there are some problems in the homework that are pure geometry problems. They're just going to give you this, you draw what it means, and then you use geometry, good old area formulas. I like it. Okay. So one of the first things we need, we're stepping into 5.3 now, is to understand a very interesting idea of if I do this. Let me just write this down and see what you guys think of this. Okay. Let's try to draw what this is saying and see what this means. So this by itself is pretty tricky to unpack. All right, so now my function is f of t. And again, the variable that I use there doesn't really matter. So here's f of t. Here's the t-axis going from a to x. This function, so by itself, what does that mean? How does that relate to the picture I've drawn? Beautiful. So find the area between a and x that's under this function f of t, 11, right? So that would be, so this is the unknown. This is somebody gives me this a. A could be -1, 18 billion, whatever, some number. And I want to go up how far? Up to x. So x is the thing, x is the true variable here. Let me let that soak in. F of t is a given. They got to give me that function. The true variable up here is x. So if I said g of x equals the integral from 1 to x of, doesn't matter, 2x, 2t dt. So what would g of 1 mean? Let's see if we can interpret the answer here without doing much work. Well, that would mean I'd plug a 1 in for x. That's the true variable of this thing, is the x. So really, it's saying is how much area do I accumulate if I let x change? What happens to the area? So the output is the area under this function. So this is what's known as the area function. This is the area under some given function. Right. So if what's g of 1 going to be? It'd be the area from 1 to 1. This should strike you as strange. but it makes the answer easy. What's the area of I don't care from 1 to 1? 0. Yeah, there's no width. So there can't be an area. So the integral, if I have the same number on the top and bottom of this symbol, the answer is going to be 0. It's dead on arrival. There's no width. How could there be an area? It's just a straight line then, right? How are we doing so far? That's a good base rule to get down. So what would g of 2 be? Yeah, integral from 1 to 2. 2t dt. You guys try to draw that out. See if you can't tease this answer out. Draw that situation out. Yes, sir?
Would you be able to say does not exist also, or no? Or zero?
No, it's not that it doesn't exist. It's just 0.
Yeah.
So I like the way you're thinking. There is no area. So in a sense, the area doesn't exist, but it is officially 0, right? It's still kind of like a limiting process. Yeah. So what would this be? This would be from 1 to 2. At 1, what's this function? 2. Yeah, so at 1 it's 2, and at 2 it's 4. It's crazy. So I want to know this area. It's a linear function, right? It's a nice straight line there. What shape is that? It's got 2 parallel sides, and the other 2 sides are not parallel. That is a very strangely shaped trapezoid. But still, it's a trapezoid. That's the official rule of a trapezoid, is 2 parallel sides, 2 non-parallel sides. You think of a trapezoid, you think this. But so all I got to do is, and now that's what that is, just turn that way. Oh shit. Now what's the area of a trapezoid formula? That's the formula for the area of a trapezoid. One half times, how many bases are there? There's really 2 of them. There's this base and that base. So it's b1 plus b2 times the height. Which is the distance between the 2 bases. I think we talked about this before, didn't we? Did I show you the circle, or just that right? It's a bad part about teaching 2 classes. So how long is this base? 2. How long is this base? That's crazy. So I got 1/2, 2 plus 4, times the height, which in this case is 1. So you might need to use the area of a trapezoid formula in your homework somewhere. So here you get 3. Half a 6. So this is 3. So you can see how I can start to graph the g function. For an input of 1, I get an output of 0. For an input of 2, I get an output of 3. I could make a table of values if I want to, and graph the g function by itself. I like it. So, yes?
Do we have to memorize area of a trapezoid?
It really is one you should know. It's the way I remember it is 1/2 base times height for a triangle. Here's a beheaded triangle, so it's got 2 bases, so you just put both bases in to be fair. That's one way to remember it. But I'd give it to you probably if I asked you a question about it. You really should know. In your homework, you can access whatever the hell to look up area formulas, yeah. So this is a function. This people focus on too much. That's some given thing. That I know that's a function too, but this is the true variable is x. That's the true variable in this case. T is what we call a little middle guy. He's the dummy variable in the middle. All right, now watch this. Let me see how I did this. If I wanted to know, then now if this is a function in its own right, how could I figure out the derivative of this function? I mean, that's what we've been doing, right? We've been doing derivatives of every damn thing. Trying to figure out derivatives of functions. Here's another function defined on something we just learned about, this area formula, which now has this symbol going for it, right? The symbol is the area under a curve from something to something. It creates its own function. What is its derivative? Does it have a derivative? It should. It has to. Okay. So let's see. Let me show you this. So how do I start to figure out the derivative of this? How did I start to figure out the derivative of the other functions from the first place? We use something you wish would never come back, but it's just going to come back for a little bit. The limit definition, right? So what do I allow to happen to start this off? What is the limit definition derivative? Let's start there. So if I have a function g of x, what's g prime of x officially defined to be? The limit is h approaches 0. Does this sound familiar? Of? Over h. I like it. Nope. All right, this should sound at least vaguely familiar, if not painfully familiar. Yeah, I love it. So you guys have every, like I said, how long did it say it's coming back for? Just for a second. We have to use this idea every now and again. When we hit a new function, or if we're trying to use something to prove something with derivatives, you have to come back to this. All right, so this is a major thing. We've never seen a function like this before, ever. I mean, this symbol, we just recently came up with a reason for this symbol. So you certainly have never seen this function before. So its derivative might be weird. And yes, it's a little funky to work out, but its derivative is stupid nice. All right, now watch. Here's how we're going to look at it. So over here on the picture, this is g of x, right? That's g of x. Is that cool? Okay. So on top of that, where would g of x plus h go? How would it look? So g of x here is this area. So really what I'm asking is, how much does the area change by if I go out by how much more? So here's g of x. What's the other piece I need? H. G of x plus h. So I'm going to put right here, what's this going to be? No, h would be here. This is x plus h. That makes more sense, right? I want x plus h as an input. So this is what x plus h is. And now now I went way far, didn't I? I went way far out. H is going to 0, so it's stupid close to this. In fact, I think of it like putting a piece of tape on top of this, right? If you put a piece of tape on top of something, does it really change its dimensions at all? Not really, not truly, not in terms of what we care about. So here's what, let's say this function just keeps going. Here's x plus h. So this would be the extra amount added on by x plus h, right? This is the area that's added on. Is that cool so far? I mean, that's by itself isn't that big of a deal. If g of x is the area out to x, g of x plus h is just going to be a little more area. And now, how much more? What is this? Let's figure out what this is. An expression for this. Well, how do I approximate that? This is going to feel very much like that rectangle thing, which, by the way, I don't think I used the official word for that. The whole rectangle process is called using Riemann sums, named after Riemann, right? Yes, he did. But watch this. So I can do something very similar. How do I approximate this area? Well, I make a little rectangle. I'm going to do it using this endpoint here. So what's the height of this rectangle? What's the height of this rectangle? How tall is this rectangle? That sits right on the x input. How tall is it? F of x, I like it. And how wide is that rectangle? H. So how much did the area change by? If I take g of x plus h minus g of x, it should equal the area. So this is approximately h times f of x. I like it. All right, let me stop here for a second. Let me let you guys. So again, it's all just about areas. We use rectangles to approximate areas, especially when we're letting the size of the rectangles get really small. That means our approximation becomes perfect in the limit. How are we doing? Yes, sir.
You did a approximation equals sign?
Yes. Total. I really want you guys all on board. Is everybody cool with this? From here to the first purple line, that's g of x. Is that cool? That's by definition. So that, by definition, has to be cool. I went a little further out, and I'm curious. The slope, the change in g of x should be how much did the area change over how much did I move? Yeah, what's the derivative of position? Well, it's how much the position changed over how much the time changed. That's the slope. How we do it? I mean, that's rate of change. So it is, how much did the area change? Okay, the area changed by this much. Approximately. But what's going to happen to my approximation when I'm going to do this eventually? What's going to happen to my approximation is to let h go to 0. It's going to get more accurate. What part of this is making it not right? Is I don't know if that's the real height all the way through this whole thing. This could be going up, it could be going down. So using f of x as the height is incorrect, more than likely, right? Because it's not just a constant height through the whole region. But if I let h go to 0, then that is the height. F of x will be the height. So it is just like putting a piece of tape right there, because it doesn't make it look much, but that tape kind of represents that area amount change, right? It's related to the idea that the area of a circle is pi r squared, but the derivative of a circle with respect to radius is 2 pi r, which is the circumference. It's equal to, if I put tape on the outside of this thing, it would have this much area. That's how much area it would add. It's that same idea, except now I'm applying it to this picture of a function, but it's still a thing of area that I'm working with. Okay, so. Is everybody with me, though, that this rectangle definitely has an area of h times f of x? That f of x is used as an approximating height. And why is that a good thing to choose? Because I'm letting h go to 0, so eventually it will become the height. As I go to 0, it's going to become the place everything's happening. And sure enough, now watch. This is too good to believe. I'm sure you guys see, maybe, where's this going? If I divide by h. So in the limit, as h goes to 0 of this, I get, it's f of x. G prime of x. If g of x is this, g prime of x is this. And if anybody knows any calculus at all, and you know, and you're like, well, integration just means take the antiderivative. It's not an immediate thing, but that's exactly what we just figured out here is if the derivative of g is f, and g is the integral of f, there's a connection between integration and antiderivatives here, right? How does g relate to g prime? G prime is the derivative of g, so g is the antiderivative of g prime. You guys with me? And if g prime is f, and I took an antiderivative of this to get here, that must mean I took an antiderivative of this other side too. So if g prime, I really want you guys with me, is f, and I take an antiderivative of this side, but what's g of x? That means that this somehow is an antiderivative of f. Notice how I said it very carefully. Is an antiderivative. I like it. So that's right there as our first beginning look at the connection between antiderivative and integral. Integral is specifically the area under a curve. Antiderivative is just undoing the derivative. If you just look at it at a very surface level, there's no reason those should be connected. If you start thinking about it any at all, you're like, there should be some kind of connection. But from the surface, it's like, why the shit would they be connected at all? Yes?
So you can basically go like back and forth antiderivative.
Well, you have to be able to, right? Like, you can add 2 to both sides and you can subtract 2 to both sides until you go insane, right? But I just wanted to make sure everybody saw this result is a huge result. Now, on the surface, how do I use this thing in a concrete example of just this? And real quick, this thing we just did, this result, that g prime of x, if g of x is f of x, that result is called the fundamental theorem of calculus part 1. What I call FTOC, right? FTOC, fundamental theorem of calculus. Sounds a little important. So this is FTOC 1. Says this: if g of x equals the integral a to x f of t dt, then g prime of x equals f of x. Okay. Now, let's look at a concrete example of this in action. On one level, this is just another derivative rule. To be honest, I want you to realize this. There's several different levels of this. Here's a function. Here's this derivative. Okay, it's another derivative rule, but there's a lot more to this. This is huge. It's kind of like connecting the next half of this well, not half. We only have 2 weeks left. But the next series of things we're going to talk about. So let's look at a concrete example. Please, dear God, Jeff. My G is all funky. It's got a little tiny head. Sure. And I know all too well how the connection can be lost when you start doing problems, how to really apply this thing we just did. Notice how if the g of x is the integral from some number to x of some function, then the derivative is going to be that function evaluated at x. So do I have that in the right setup? Is that the right setup for the function? Yes, totally. It's like totally true. So then this means that g prime, here's where people get all confused. Don't put no cosine down or something. I'm not taking the derivatives of sine. Now that I know that this integral symbol is related to antiderivative, that's really what this result means. It's sort of like cubing a cube root. They just kill each other. So when I take the derivative on one side, it should kill this symbol, and that's exactly what happens. So I do get sine, but where's sine evaluated at? X. All right, so on that, okay, that's nice, right? And again, this is just straight derivative of a function. I haven't put any chain rule stuff in there. I haven't done anything else freaky to you. So that should feel nice. That function does not change because what you're doing is you're canceling this stuff. That's really what's happening. The big mistake people make is they do this, and when I put some funky ass stuff in there and they waste time just trying to do derivatives, I'm like, no, the derivative doesn't survive to get in there. It dies when it kills this thing. Does that make sense? They're inverses of each other. All right, let's try another one with a little more to it. If g of x equals integral of 7 to x squared of a natural log of cosine of 5x minus x to the x. Screw all the x's. Take all the x's. T. Now real quick, I want this to make sense. So I started making a mistake putting x's there. Part of my brain immediately rebelled because you can't have the variable that's in here be the same as what's out here. That doesn't make sense. So again, it doesn't matter what I put in here. Do not waste time taking derivatives of this. Do you want to take the derivative of this? Yes?
So right now, t would basically be like y, or no, I mean, t would kind of be like x right now.
T is the x-axis, yes. So if you want to look at this, what this is saying is it's from 7 to x, and whatever that function looks like, blah, 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 right? So it is the area between 7 and whatever you want. And it even goes that way too. X could be over here. It would just be negative then. Okay, so what do I get when I take the derivative? What's the only thing that's different from what I just did? Sine doesn't matter what shit. I could have put any function in there, and it would have been, that would have worked the exact same way. Doesn't matter what that function is. So that function doesn't matter. I know that's different, but what's the real different thing?
T to the t.
Again, whatever this function is, doesn't matter. Real quick, over here. If I would have said g was -2 to x square root of x of t dt, what would the derivative of that be? It would just be square root of x. Did it something t becomes something x? Something of t, yeah. So what's the only difference? It's x squared. Is there a function inside of another function? Yes, there's an x squared where there's normally an x. So that would be a what rule? Chain rule. This is really weird to us. We're not used to our input like sitting on top of some stupid little shape. I'm up here. You know, we're used to it being inside of a square root, inside of a sine, or just sitting there with a little power on it. We're not used to the input being like up here. But this is just like something with an x squared in it. You've got to use chain rule. So what's the rule for this symbol, the integration symbol? What's that rule? You apply that first, and then you multiply by this guy's derivative. So this becomes the same shit evaluated where? What's the rule say? What do we do here? We rewrote we made this become evaluated at that. Bam. So what does this become? Natural log or cosine of 5 x squared minus x squared to the x squared? Because that's the rule for this symbol. What is the rule? Rewrite this with that in it. That's the rule. Now comes the chain rule's turn. It says, oh, this dude is in there. He gets a turn. Never at the same time. You never do two rules. Don't put a 2x here. You're doing two things at the same time. No. They each get their own separate turn. This is times 2x. Bang it. So it doesn't matter what's here at first. Just like chain rule always is. It doesn't matter what's in there first. Right? If I said take the derivative of sine of, I'm not going to tell you. What would that be? What's the derivative of this? Come on. Cosine of, I'm not going to tell you, times the derivative, I'm not going to tell you. I mean, that's... So what's the first step? It says, don't give a shit what that is. Worry about that. Don't give a shit what that is. Worry about this. That becomes that with that in it. I like that sentence. That becomes that with that in it. So the derivative of this, the integral, becomes the function inside evaluated at that endpoint. And then the inside gets a term. Then you do times 2x. So I could put, I could put sine x up here, natural log, whatever the hell. Right? Maybe. All right. Here's the ultimate funky example of this. Become a G. Let's make this natural log of x. And then this doesn't really matter. Secant of 3x. Doesn't matter. Make it a T, Jeff. There you go, buddy. No, there's something really wrong with this. It's not in the right form. What if did they give you that? Well, I'll give that to you. I guess they didn't give that to you before. Nope. Okay. So this says go from 5 minus x to natural log of x. But what is supposed to be here? Just a constant, right? Some constant. So there's a fundamental problem with the form of this. I don't have a rule for this directly. If it was a constant to a function of x, all day long I could do that. Whatever function of x you do there, I'm just going to multiply by its derivative at the end. Who cares? But this is fundamentally wrong. I can't do something to it the way it's written. I need to rewrite it somehow. So here's the thing that we have to start getting used to. And I know this whole thing is getting used to integration. Let's say there's a point in between. Let's call it A, or whatever you want to call it. Or you can even pick a number. It doesn't matter. So I can rewrite this as integral 5 minus x to a of this stuff plus the integral a to natural log of x, this stuff. From there to there, added to from there to there. Doesn't that sound familiar to what we did last time? So the area under this whatever, I can break it up into the area from here to here, and then the area from there to there, and add those two together. Now there's still something wrong with that first integral. It's not quite right, it's not quite the right form. Can somebody at least tell me what the problem is, and then I'll show you how to work with it. What's wrong with that first integral?
Variable on the bottom?
Yes. There's supposed to be a number on the bottom, variable on the top, which is a difference. It is not in the right form still. Because what's the form say in f-talk 1? It says a to x, integral ft dt, blah, blah, blah. Then it can do something. So they can't do something to this yet. The other part's fine. So real quick, watch this. Side note. If I had the integral from a to b of some function, and that looks like this. How wide is this? How wide is it? B minus a, right? Is that cool? B minus a. So how does this relate to this? How does that change things? Or does it? Yes. Because now it would be a minus b, but a minus b is what kind of a number? Negative. So it'll be the negative. So this is equal to negative this.
Is there a reason why we didn't do that at the beginning? To make 5 minus x a constant?
I can't make 5 minus x a constant. I can't. Oh, I see what you mean. Oh, then the other integral would have had a problem, right? I see what you mean. Yeah. We totally could have done it, broken it up the other way, but it would have still led to the same kind of problem, right? Even then, even then, from the beginning, you would have had to do some negative stuff because you can't really just put an a here because then that's like outside of this range. What does this integral say? It goes from this to this. So I really want to pick an a that's in there to break up that area. If I pick an a out of there, it doesn't make sense. It doesn't make physical sense. Because then I'm dealing with areas that I don't even care about in the original integral. Okay, maybe. So now this is equal to negative integral a to 5 minus x. This business plus integral a to natural log of x. This business. And now I can do the derivative. So g prime, let's see if we can handle this. Some of you guys might see ahead a bit and notice I don't need what I'm about to write, but I'm not going to do that yet. So a negative, what's the derivative of integral secant of 3t dt? What do I do? It would be secant of 3 times 5 minus x. Whatever's there goes in. Times the derivative of the inside. What's the derivative of this? Negative 1. Good old chain rule. Plus, see, those negatives cancel then. And then this is the same idea, but now it's secant of 3 times ln of x times the derivative of ln x, which is 1 over x. Okay, so to clean this up a little bit, this is secant of 15 minus 3x plus secant of 3 ln x over x.
So where did the negative one come from?
Oh, here?
Yeah.
It was the chain rule.
Oh.
The derivative of this would just be the negative 1. Cool. I like it. It's so damn easy to forget. So don't blame me too much. I'll still take points off. It's easy. It's a real easy mistake to make. So really to summarize, I mean, that was just little detail stuff about, since we've identified a function and we know its derivative, we can now do all the rules to it. Do you follow what I'm saying? All the rules still apply, still a function, all the rules have to apply the same way they have before. Then there's a little bit of detail about how these things kind of work, how to get it in the right format, but it's still another little detail. I know the details kill you. One more little thing and then we'll take a break. Shoot, which one I was going to do right now? Oh, I wanted to summarize some stuff we've done here. The integral a to x f of t dt. I want to write it like this just to really show you what we've discovered. Now, There's a lot more to the proof of what I'm about to write down, but to be honest, the entire thing keeps coming back to this point. If I take the antiderivative of both sides, right? So, let me see, how do I say this? Let me. So very cool with it. I mean, this is what we just figured out. True? I like it. I like it. Let's see, maybe I should just do the, trying to make something up on the go. All right. Now, here's the funky thing. When I take antiderivatives of things, so let me ask you this. If, here's a big idea we're about to apply in a bit. If f prime of x equals g prime of x, just in general, if that's true, is it necessarily true that f of x equals g of x? We have a really easy example. Remember, what's the fundamental meaning of derivative? Fundamental meaning of derivative. One word. Yeah, slope. Right? And now we know that slope can change. The minute you move from a point, the slope changes, but it's still, the derivative tells you the slope at any point you want to know. So that's why it is a function, because it has to change as I move. So the slope no longer is just a single number, it's a function, because it changes. What's a really good example about two things that have the same slope, but aren't the same thing? Totally. So like 2x plus 1 and 2x plus 2. Do they have the same slope? Yes, but they are not the same thing. Is that cool? Well, sine has a slope of cosine, and cosine has a slope of negative sine. So, well, you see where you're trying to go, but it doesn't quite work. So their relationship then is this. F of x equals g of x off by a constant. Is that idea by itself cool? I mean, that's the whole idea that we just came up. I know we can use it as a simple example about lines, but that truly is the only difference. It's just a constant, kind of place them somewhere. If I know where it's going, I don't know where it is, but I do know